Walk me through a backend system you built from scratch. At PwC, I was tasked with building a data ingestion pipeline from the ground up to process and transform large data sets across distributed environments. I led the full life cycle from system design and architecture decisions through implementation, rollout, and ongoing production support. I made deliberate decisions around reliability and failure handling from the start, which meant the system required minimal firefighting after launch. That kind of 0 to 1 ownership is something I have done multiple times and genuinely enjoy. The follow up question by the interviewer could be, what is the data ingestion pipeline? So you could basically explain what the system was, why it was needed, what you designed, the tech stack, the hard problems you solved, and the result. So let me start with the tech stack. We used Python for the pipeline logic, Apache Kafka for event streaming between stages, PostgreSQL as the destination data store, and AWS infrastructure, S3 for raw data handling, Lambda for lightweight transformations, and CloudWatch for monitoring and alerting. Everything was containerized with Docker and deployed through CI/CD pipelines. What the system was, at PwC, I built a data ingestion pipeline for a large enterprise client that needed to consolidate data from multiple source systems, which are databases, third party APIs, and flight file exports into a centralized data platform for analytics and reporting. The data volumes were significant, running into tens of millions of records processed daily. Why it was needed? The client had siloed data sitting across different systems that could not talk to each other. Business decisions were being made on stale and incomplete data. They needed a reliable automated pipeline that could pull, validate, transform, and load data continuously. I designed it as an event driven pipeline with clear separation between ingestion, validation, transformation, and loading stages. I chose this approach because it made each stage independently testable, scalable, and replaceable without touching the rest of the system. As I explained, the test stack is Python for the pipeline logic, Apache Kafka for event streaming between stages, PostgreSQL is the destination data store, and AWS infrastructure such as S3 for raw data handling, Lambda for lightweight transformations, and CloudWatch for monitoring and alerting. Everything was containerized within Docker and deployed through CI/CD pipeline. The two biggest challenges that I faced were data quality and failure recovery. Source systems sent inconsistent and sometimes malformed data. I built a validation layer that quarantined bad records, logged them with full context, and triggered alerts rather than failing the entire pipeline. For failure recovery, I implemented idempotent processing so that if any stage failed and restarted, it wouldn't create duplicate or corrupted records downstream. The pipeline went live on schedule, processed millions of records daily in production, and ran with minimal intervention. It became the foundation the client's analytics team built reporting dashboards on. That project is a good example of why I really care about reliability from day one. Retrofitting failure handling into a live system is far more expensive than designing for it upfront. Now, they could also ask you what is idempotent processing. You could say processing designed so that running the same operation twice produces the same result, critical for safe retries and failure recovery. Finally, I am concluding with the test stack once again. We use Python for the pipeline logic, Apache Kafka for event streaming between stages, PostgreSQL for the destination data store and AWS infrastructure, S3 for raw data handling, Lambda for lightweight transformations, and CloudWatch for monitoring and alerting. Everything was containerized in Docker and deployed through CI/CD pipelines.